Hi, I'm Steve Bourne from Atkins. I'll be presenting using City Simulator to prepare for COVID-19. What is City Simulator? In general, it's a map-based decision support tool. It helps communities understand their vulnerabilities to future disasters, typically disasters focused on climate change, and it allows them to find the most effective mitigation and adaptation actions. How does City Simulator work? It's a detailed digital twin that we build of a community, including system users. So we're like focused on agents. It's an agent-based model is what it's called. That means we synthesize a population of avatars that matches the real population in terms of demographics, gender, and so on. And then we can simulate them moving around the city. What do they move around in? That's system infrastructure. So parcels and buildings, roads and rail, all the utilities, natural systems, rivers, soils, wetlands, and so on. We also have system control in this digital twin. So what is the zoning? What set of rules governs what can be built on and what can't? What are the political boundaries? What's the building code? And so on. Once we have that digital twin, we can do a simulation. So we typically simulate from 2020 to 2050 in this nested loop pattern that you're seeing. The annual loop here, this is run once a year during our simulation, and it simulates urbanization. So it starts out with, economy. How well is the economy doing? That gets translated into new commercial development, where we literally put buildings in the landscape in vacant lots. We then say those buildings have to have businesses and workers in them. Those workers need to have homes, new residential. So we put that across the landscape as well. We'll then add infrastructure, roads and pipes and so on to connect all these. And then we'll look at, what's the impact on floodplains? What's the impact on ecosystem services? What's the carbon footprint impact of doing that urban? On the daily loop, this runs once a day, and it's looking more at did a storm occur? Which buildings were impacted, and how long is it going to take them to recover? It also looks at daily activities that occur when disaster hasn't occurred. Things like travel, commuting, working, commerce, shopping, and so on. So we get a full simulation of all the activity that happens in the city over time. We also have metrics we're measuring as this simulation is going on, and they typically fall into the triple bottom line. So economy, people, environment. For economy, we're measuring stuff like productivity. How much are people working? Storm damage, what's the total damage across the city due to storms? And when we do mitigation and adaptation, we're looking at, what's the return on investment of those actions? For people, we're looking at how many days do people spend, displaced from their home because it's being repaired? How many times can they not get to work because of, hurricanes occurring and so on, and flooding streets? We'll look at low to middle income populations, heat exposure, those types of metrics. And for environment, we look at carbon footprint, pollutant loadings, water quality, and so on. This is what it all ends up looking like when we actually apply the tool. This is Hollywood, Florida, a town just north of Miami. And we've configured the tool. Again, it runs in ArcMap, and we've configured it to visualize as it runs. And this really helps out with, understanding, what's the impact on the city, the real impact of future climate. I'm going to pause it and just explain a couple of things here. The colored roads here, that's tidal flooding. So that's like the king tide flooding we hear about, impacting this set of roads over here close to the Atlantic. The yellow dots you're seeing, those are new buildings, new commercial and residential buildings occurring. And then the red line here you're seeing, that's a forecast of rainfall built from global climate models. When a large rainfall event occurs, this is an 18-inch rainfall, that's a big storm. We can see that the workforce engaged, the green line, drops off, and then it takes it a while for it to recover as people's homes and workplaces are repaired and they can resume their normal productive lives. So let's go ahead and continue on the video. You can see there's a big event here, 22-inch storm, and the black dots you're seeing, these are building sustaining storm damage. So you can see that's a big storm. It affects the whole city. So that was a brief review of City Simulator. The disasters that we model within City Simulator have been focused on climate change for the most part. Things like sea level rise, heat waves, hurricanes, storms, droughts, and so on. One of the disasters that we had on our roadmap, though, was epidemics. And with COVID starting up and becoming clear that it was going to be a global problem, that skyrocketed to the top of our list. We jumped into it, right in the March, April timeframe, and went very quickly through developing a module that simulates epidemics within City Simulator. It's based on the so-called SIR model, where you partition out your population into buckets of susceptible, infected, and recovered. And to model the infectiveness, in other words, how quickly do people move from susceptible to infected, you'll use typically a mathematical approach, which is governed by this kind of equation. So, you're looking at the number of contacts people make, the person-to-person infectiveness. So if you do make a contact with a person, what's the probability you're going to get infected? And the percentage of the population that's infected at the current time. For recovery, that usually comes down to, how long does the disease take before you've hit that, immune state where you're not likely to get it again. If you apply that model, say, to the United States, this is 380 million people, you get a result like this. So the susceptible orange line, that starts out at the full population and drops to 0 over time as the infection happens. The recovered line moves up to the full population, and the gray line here represents the infected population. The peak of this is very important. When we talk about flattening the curve, this is the curve that we want to flatten. So when it came to, how do we actually model this in City Simulator, we said, all right, let's, because we actually have a contact model already built in, we're modeling agents moving around. We don't need to model this sort of, averaged bulk approach to understanding who's infected and who isn't. We can actually look at each individual agent. So we got rid of that. And we brought in the commuting that happens on a daily basis, the journeys of people from place to place. This is already being modeled in City Simulator. So, people are at home, they're in contact with their families. They may go out, they may stop during their commute, get gas, go to grocery stores and so on, all opportunities for infection. They may spend 8 hours a day at work, interacting with their colleagues. They may, stop somewhere else on their way back, and then they're back at home. We have, all of this being simulated already within City Simulator. We also have to think about, okay, we have it being simulated, but, what type of contacts are really happening? What's our contact model? And we came up with 3 different modeling approaches or situations that we have to model within the tool. Those include direct contact, people coming in, touching each other's skin, and, being within the same, close environment. There's proximal contact. So in other words, how close are people getting to each other? We have our social distancing rules of 6 feet, say 6 feet apart. We want to model how close are people getting to each other and in what situations, so we can get a good idea of who's being infected. And then we have, the fomite idea, so surface contacts. Is the gas pump that you're picking up right now, who picked it up last, and what was the probability that they were infected, and what's the probability that the disease is now active and will infect you? So we had to consider all those in our simulation. The advantages of this agent-based approach, we reasoned, are, it removes the averaging effect of using bulk infection model. And it provides you, therefore, a much higher level of detail. It's an automated contact tracing within the simulation at the level of the individual. So, we can take any simulation and sort of trace back where the contacts happened and understand, how the dynamics of the infection are working, and hopefully gain information from that to apply to the real situation. We can pinpoint hotspots across the community. Remember, we have a model of a real community, every building, every parcel, every road, and so therefore we can find places where high spreading can occur within the community. And then we can estimate impact of potential measures. This is probably the best part of it, is that with City Simulator, we can say, well, what if we clean the gas station pumps once an hour? Or what if we implement lockdown and so on? How effective will that be? So we jumped into it and built a model. We used the virtualization capability within City Simulator to create a virtual model. So this square diagram you're seeing, that's actually our model. That's the map of the city that we built. It's called Optima. It has about 100,000 people, and it has the yellow dots and red dots you're seeing there. Those are commercial and residential buildings. Red is commercial. You can see there's a main street, a central business district on the southwest quadrant here. The red line is the main street. The reason that we used a virtual city and not a real one was there is some, definite sensitivity with announcing, hotspots of potential disease spread in a real city. And we wanted to avoid that in favor of just being able to calibrate our model and make sure that it's working correctly. Since Optima is a city simulator digital twin geodatabase, it provides the same level of detail as a real city simulator database of a real city. And here's an example. I've zoomed into one of the commercial buildings in Optima, selected it, and said, give me the commute footprint. And the cyan lines here show every road segment that's taken by the people who work in that building. How do we know that? Here I've run a query where I'm showing every person who works in that building, and you can see their gender, their age, and so on. And you can see the commute footprint, like the IDs of the road segments that person takes to get to work. So it's a very high detailed model, and it does very well as a result in doing epidemic modeling. Our initial experiment, the assumptions we made, and again, it's important to note that these are assumptions. We were building this in the early days of COVID, and we didn't really have a whole lot of data that we could calibrate to. But the assumptions that we made here were a new infected person enters the city every 10 days. It's a 14-day period for recovery and to become immune. So once you're infected, it's 14 days before you are recovered and immune. It's a 5-day period before you, start to show symptoms. Everybody's asymptomatic for the first 5 days. And then there's a 50% probability that you will become sick and not able to work if you are infected at once you hit the 5 days. Probability of contact and transmission is detailed in this chart right here. Basically, the take-home point here is that, if you're at home with family, you have a much higher probability of contact and transmission than if you're working in a building, say, and someone in another business, another office has the disease. This is what the run ended up looking like. You can see here's Optima in the map here. And the blue dots are, a building with an infected person. So you can see, within the space of 8 days, we get a massive impact. And, most of the city is infected. And in fact, we're at about 70, the peak goes to about 76,000 people infected at the same time. Remember, Optima is about a 100,000 person city. So, this is a huge impact. We wanted to try a mitigation measure with epidemics. And we picked social distancing. We made several assumptions here, and we also set several modeling parameters to create a set of runs to find out really how effective social distancing can be within our model. The assumptions are shown here in the chart. We basically assume that the probability of contact and transmission drops significantly if social distancing is being performed by the population. The options we explored were the start time. So when do you start it after you've discovered 10 cases, 50 cases, 100 cases? The duration of the measure. So how long do you apply social distancing? 14 days out to 84, and the compliance of individuals. 50% of individuals comply with social distancing, 75%, 100%. The metrics we looked at, the primary one was peak infection cases, because that's really the part of the curve that we want to flatten. But we also looked at, time to peak and the duration of the pandemic. Here's the result we got for social distancing. The chart on the left is the base run. We've seen that before with the 76,000 peak cases. Social distancing is on the right. We use the case where it starts when 10 cases are discovered, and it is in place for 14 days, and it's 50% compliant population. So the result that we get is that there's 63,000 peak cases, which is a drop from 76,000, but it's still far too many cases for the medical facilities within the town to be able to handle. Expanding out to the full set of runs, you get the chart that we see here. On the left is peak cases, and on the bottom is the number of cases discovered before you start social distancing. The colors indicate the duration of social distancing, so from 14 days out to 84. And the bars, the top of the bar represents typically the low compliance case. So 50% compliance, and the bottom of the bar represents the highest compliance case, or 100%. The main takeaways here are that, allowing a few cases in the beginning before you start social distancing creates kind of a seed group, and the infection can spread, but in a very controlled way, resulting in lower peaks. Also, we can see that, a large conclusion here is that if we try, all the different options we had in our experiment, we can eventually, reduce the peak by about 50%. Take it down from 76,000 to about half of that. We couldn't really do any better than that. We found that compliance was the variable that moved the needle the most in our runs. These charts show that as you move from 50% to 100% compliance, the peak drops from 63,000 cases down to about 35,000 cases. The takeaway here is that, if we can get that high level of compliance, it's possible to and extend the duration. We only tested out to about 84 days. If we just say we're going to extend the duration of the social distancing until a vaccine has been found, then we end up with, what starts to be manageable levels in terms of number of cases at any given time. This is what the run actually looks like. Compared to the first video I showed, you can see that there's far fewer buildings at any given time that are impacted, and the city is probably able to continue to operate here with this level of infection. Note that these peaks are lower than the 70-day duration case, and that's because what we've said is just continue applying social distancing until a vaccine has been discovered. To wrap things up, I'll look at ongoing modeling enhancements. We've been looking at multi-disaster. So what happens when a pandemic and a hurricane happen at the same time? We're finding out some really interesting stuff around shelters. And specifically, if you're 6 foot social distancing, how much more shelter space do you need? We're also looking at uncertainty. Really, I've been showing you one run at a time of this model, but in fact, we run it 1,000 times to estimate the uncertainty in any estimate that we're putting out, like estimate of peak cases, for example. This helps us get to best and worst cases. Place and realism, it's all about location with City Simulator. We're applying it to real cities now, and we want to increase the complexity of the modeling. Calibrating it with contact tracing data, fomite spread, and so on. Other measures are needed as well. We've tried social distancing. We're adding others in now, things like wearing masks, cleaning surfaces, and so on. And we want to really look for the ability to string measures together in series and parallel to look for 1 + 1 = 3 situations. Thanks for watching. For more detail, I'd invite you to go to our website or to contact me directly by email. Thank you.